Now let's start section 6.3, power in the wind. Since power is energy per unit time, the power represented by a mass of air moving at a velocity through area A will be equal to the power through area A is equal to energy divided by time. That is equal to 1/2 mass divided by time multiply v squared. V represents the velocity. The mass flow rate m through an area A is the product of air density rho multiplies speed and multiply cross-sectional area A. They're combining the equation 6.3 and 6.2. We can obtain that the power of wind is equal to 1/2 rho represents as the air density multiply the area cross-section area multiply V cubic. And the unit of PW is watts. The air density is a kilogram per cubic meter. A is the meter square, and V as the wind speed is a meter per second. Figure 6.5 shows the power in the wind per square meter of cross-section at 15 degree and 1 atm. So as we can see, this is the wind speed in terms of about meter per second. And this is the wind speed in terms of meter per hour, mile per hour. And this is the power of the wind in terms of watt per square meter. As we can see, the power of wind is the cubic wind speed. It's a function of cubic wind speed. Equation 6.4 also indicates that wind power is proportional to the swept area of turbine rotor, A. Area is the cross-section area. For Darius wind speed, since A, the cross-section area, is equal to pi divided by 4 multiply the diameter square. And then this shows the economics of scale with the wind turbines. Since the cost of a wind turbine increase roughly with proportional to the blade diameter, but the power is proportional to the diameter square. So the bigger machine has proven to be more cost-effective. For vertically axed wind turbine, the cross-section area A is equal to 2/3 of diameter width, 2/3 of maximum rotor width and height h, as shown in the figure 6.6. So the area is equal to 2/3. D is the width multiply the height. Section 3.1 shows the temperature correction for the air density. As we know that PV is equal to nRT. P is the pressure of the air, and V is the volume as the meter cube. So P multiplied V is equal to N is the mass of air, R is the ideal gas constant, which is equal to 8.2056 multiplied 10⁻⁵ cubic meter multiplied ATM, and the inverse of K and the inverse of mu. And T is the absolute temperature, K, where K is equal to centimeter plus the 273.15. And we know that 1 atmosphere of pressure is equal to 101.325 kilopar. Pi is a abbreviation of pascals. And 1 pi is equal to 1 Newton per square meter. 1 atmosphere is also equal to 14.7 pounds per square inch. And 1 psi is equal to 6.89 kilopar. So 100 kilopar is called a bar, and 100 par is a millibar. If we use molecular weight MW, stand for the molecular weight of gas, which is a gram per mole, then the air density kilogram per cubic meter is equal to N represents the mass of air multiply molecular weight of gas, gram per mil, multiply 10⁻³ divided by volume, which is the unit is volume is meter cube. Therefore, air density rho is equal to P multiply molecular weight multiplied 10⁻³ divided by RT. We can see that the air density is a function of pressure and temperature. This air is a mix of molecules. In the air, most of nitrogen accounts for 78.08%, and oxygen accounts for 20.95%. And air has a little bit of argon, carbon dioxide, and neon. Table 61 shows the density of dry air as a pressure of 1 atmosphere. As we can see, as the temperature increases, the air density decreases. The density ratio Kt is also decreased. The density ratio Kt is a ratio of density at temperature T to the density at the standard 15 degree. Section 6.3.2 Altitude correction for air density. A horizontal slice of air in the column of thickness dz and density rho will have a mass rho multiply area A multiply dz. If the pressure at the top of the slice due to the weight of air above it Then the pressure at the bottom of slice, Pz, will be Pz plus dz plus the added weight per unit area of slice itself. So the pressure Pz is equal to Pz plus dz, the pressure of this area, plus the weight of this area is gravity constant multiply rho multiplies cross-section area multiply dz divided by cross-section area A. So dP, the change of the incremental pressure, is equal to P pressure Z plus dZ divided by Pz, and is equal to minus the gravitational constant G, which is equal to 9.606 meter per second square, multiply rho, which is the air density, and multiply dz. So dP divided by dz is equal to minus rho gravitational constant G. If we replace rho as a molecular weight divided by RT multiply P, therefore dP beyond dz is equal to minus G multiply molecular weight multiply 10 minus 3 multiply RT multiply P divided by RT. So we can obtain dP divided by dz is equal to minus 1.15 multiply 10 minus 4 pressure. So dP divided by dz is as a function of pressure itself. So P is equal to P0 E minus 1.15 10 minus 4 height. So we represent the pressure as a function of the height, altitude, where P0 is the reference pressure of 1 atm and H is in terms of meters. Table 6.2 summarizes the some pressure correction factors based on equation 6.13. Then we can combine the temperature and pressure correction density together. We can easily obtain the air density rho is equal to 1.225 kT multiplied by Ka, where Ka is the pressure ratio indicate as the pressure at the 15 degree as a function of altitude. So as the altitude increase, the pressure decrease. And the Kt, it shows the density ratio. Kt is the ratio of density T to the density at the standard 15 degrees. So eventually, air density rho is equal to 1.225 density ratio due to the temperature correction multiply the density ratio, pressure ratio due to the pressure correction. Now we complete the section 6.3.